Thank you very much for the invitation and for the introduction. So this talk relates to Zimin's talk this morning, in the sense that we're going to talk about symmetries in machine learning, and we believe that this is an important topic because in order to model machine learning models for the physical sciences, we believe that we should incorporate the symmetries that the physical processes have. And these symmetries are very related to the conservation laws that Zimin was presenting this morning. So due to Noether's theorem, conservation laws are related to symmetries in a specific way. These are the active symmetries of physical law, but there's also another bigger set of symmetries that have to do with the fact that when we take a physical object and we write it mathematically, then there's not a unique way to do it. There are many ways to transform it using different coordinates, units, and so on. And this gives us a very large set of symmetries that one can incorporate into your models. And we claim that models that satisfy these symmetries have better generalization properties and so on. So in this talk, I'm going to talk about two different things. I'm going to talk about machine learning functions on point clouds, in particular invariant functions on point clouds, with Galois theory. We're going to use Galois theory techniques to develop a set of machine learning tools for this. And this is joint work with Teresa and Ben and Marco Couturi. And then I'm going to talk about a theoretical framework for ML models on varying size objects, so objects of different sizes. So that was actually appeared in Aram's talk earlier, like point clouds, and the fact that we want to work with objects of different sizes. Like a point cloud typically is not a fixed number of points. The number of points can vary. Graphs, the same thing. You can have graphs of different sizes, and you want to apply the same model to all these objects that have different sizes, and how one can do that. Good. So, OK, so I'm going to talk about machine learning on point clouds, and we saw machine learning on point clouds in Aram's talks earlier today. And there's a lot of work that look at machine learning on point clouds from different perspectives, with applications to chemistry, astronomy, material sciences, and so on. We saw computational biology as one of the applications. And in particular, the machine learning on point clouds that we want to look at now, different from Aram's, is that we want functions that are invariant with respect to orthogonal transformations and permutations. In his case, permutations was invariance that he wanted to look at, but orthogonal transformations was not something that he mentioned in his talk. So the motivation for this talk, for this project, came from a conversation with Kay Story-Fisher, who was a PhD student here in New York. And basically, she was looking at these regression problems on point clouds coming from dark matter simulations. She had dark matter simulations that were very massive, and she wanted to use those to infer properties of other simulations that were more expensive, like hydrodynamic simulations. And she wanted to use the cheaper dark matter simulations to infer some properties of galaxies from the more expensive simulations. So basically, it was a regression problem on point clouds that, in particular in this case, the point clouds, the intrinsic properties of the point clouds were invariant with respect to doing translations or rotations or permutations of the points. So how can we do these machine learning models? And in particular, something that she had was massive point clouds. So we want to be efficient. We want to scale linearly, if possible, with the number of points. So in this setting, mathematically, we can write it as we have D is our points, our endpoints in dimension D. We can write it as this matrix over here. And so we want a function that takes these D points and endpoints in dimension D and outputs, say, a real number. And we want it to be invariant with respect to orthogonal transformations, which are translations, rotations, and reflections, so ED. So it's OD plus translations, and also permutation invariant. So in order to implement the translations, what one can do is you can take your point cloud and subtract the center of mass. And that gives you kind of like one representative in the orbit of all possible translations of all these point clouds. So it's something that in machine learning, equivariant machine learning is known as canonicalization. That allows me to identify one point per orbit of in this space, and allow me to write a function that is invariant. After we model out by the translations, we can look at the orthogonal transformations. And the orthogonal transformations are rotations and reflections, and this can be dealt with the first fundamental theorem of invariant theory that tells you that any function that takes n points in Rd that is invariant with respect to orthogonal transformations, which means that you apply the same orthogonal transformation to each of the n points in Rd, can be written as a function of the inner product of the input vectors. So, and this is an if and only if. Any function that you can write as the inner product of the input vectors is invariant with respect to orthogonal transformations. That is kind of obvious, because if you take the pairwise inner products, then that is invariant with respect to orthogonal transformations. So a function of the inner products is going to be invariant. And then the fundamental theorem of invariant theory tells you that those features are sufficient to write any function that is invariant with respect to orthogonal transformations. And then that is for the orthogonal transformations. You have the inner products, but then you can use the same theory to characterize invariant functions with respect to other simple Lie groups, like the Lorentz group or rotations, etc. And you can extend this to write the equivariant functions, but that's not what I'm going to talk about today. After we figured out the orthogonal transformations and the translations, now we have to look at the permutations of the points. And so, so basically you have your points, your data points here, written as this matrix, and you're acting by orthogonal transformations on the left, just multiplying by orthogonal transformations which are in d times d. And then you multiply by permutations on the right, which are permutation of n points. And so a function, you know, that is invariant with respect to orthogonal transformations if you write it in terms of the inner products. So you can write it as this B transpose B. And now if you apply an orthogonal transformation to your points, then if you apply a permutation to your points, then the permutation of the rows of the columns of B maps to a permutation of the rows and columns of B transpose B, sorry, right? So then if you look at the matrix of inner products, if you just permuted the columns of B, in the matrix of inner products, you are permuting the rows and the columns. And the invariance with respect to that action of permuting rows and columns is the same invariance that graph neural networks look at, right? So this is the symmetry of GNNs. This is a learning of graphs. So GNNs are showing up for now. They'll show up later. OK, so how do you do that? Well, you know how to do GNNs, but we're not going to use GNNs. GNNs will come out later. We're going to use invariant theory instead of GNNs. Sorry about that. And the reason why we're going to use invariant theory is constructing this constructing the graph is n squared. But we're going to be able to do it in order n times d, which is what Kate wanted for her project. So, and we're going to use some interesting mathematical tools for it. So it's going to be interesting. OK, so the idea of how we are going to parameterize these functions that are invariant with respect to permutations by conjugation is by using Galois theory. The idea is the following. If you have your matrix of inner products, and then you apply a permutation that permutes rows and columns, then any diagonal element is going to be sent to another diagonal element. And any off-diagonal element is going to be sent to another off-diagonal element, right? But not every transformation that does that is consistent with permuting rows and columns. So we can say that the group of permutations acting by conjugation is a subgroup of the bigger group that basically sends diagonal to diagonals and off diagonals to off diagonals. And so if you know that this group, if this group is smaller than this, then the invariant functions with respect to the smaller group is a superset of the invariant functions with respect to the bigger group. It's just like the inclusion between the groups and the invariant functions goes the opposite way. That's part of Galois theory. And so what we can do is we can write the invariants with respect to the bigger group and then extend them to get the invariants with respect to the smaller group. And that's what we are going to do. So for the bigger group, that's an easy group to work with because it's just the product of two permutation groups. And we know that like how to write the invariant functions with respect to just permuting the elements. You can think of, like if you're coming from machine learning, you can think of a function in sets, like a deep set. Like a function in sets, you can think of function in sets of the diagonals, function in sets of the off diagonals. That will allow you to universally parameterize all the functions that are invariant with respect to the large group. And then you can extend that to the smaller group. So what Galois theory says in this context is that if we can construct a set of invariants that are only fixed by the desired group, which is the smaller group, and no other bigger group fixes these invariants, then those will generate the field of invariant functions. And then the Rosen-Schlitt theorem says that the orbits that the field generators fail to identify is a small set. It's it's a set of zeros of a finite set of equations, polynomial equations, and this is an invariant measure zero closed set. So basically what we can do is, using these techniques, we can generate the field of invariant functions, and those ones will give us a result that is universal approximation everywhere except in a closed measure zero set that we are not going to characterize, but is possibly characterizable. So the idea is the following. So we have, we can order groups by inclusion. We have the trivial group inside the group that we care about, which is the permutations in n elements acting by conjugation. This is inside the larger group, which is permutations of diagonals and off diagonals independently. And then on the right side, we can write the invariant functions. So for the trivial group, the invariant functions are all the functions, just like all polynomials on entries of the symmetric matrix. Then inside that, you have the field of invariant functions by conjugation that we want to get. And inside that, we have the field of invariant functions that permute the diagonals to diagonals and off diagonals to off diagonals. Those ones we know is just the field of symmetric polynomials generated by the diagonals and the off diagonals. You can think of generated by the deep sets of the diagonals and the deep sets of the off diagonals, if you want to think of it in terms of machine learning. And then what you can show is that if you add this extra polynomial, then that extra polynomial is only fixed by this group and nothing else, nothing bigger than this inside this. And so that proves that in order to write the invariant features, I can just take the invariant features from like the bigger group and then add this little polynomial, and that would give me invariant features for the problem that we cared about. That's basically the construction. Questions, comments? So after that, after we have this like math result, we can write a machine learning model based on it using deep sets. So you know that deep sets, if you haven't seen it before, deep sets, what it does is like it allows you to write invariant functions that are universally approximating, and it's actually the universal approximation theorem that we saw by Zimming today is used in the deep sets to prove universality, the Kolmogorov-Arnold approximation theory. And so basically the idea is that a function of a set can be written as that is invariant with respect to permutations of the entries of the set can be written as a row of the sum of some functions of each of the elements of the set. And this is universal due to the Kolmogorov-Arnold theorem. And so using that, using a deep set architecture, we can define our class of functions to be computing some function of a deep set of the diagonals, a deep set of the off-diagonals, and the extra term that we constructed using Galois theory. And we can show that this architecture can universally approximate invariant functions on symmetric matrices outside an invariant closed measure zero bad set. That's the idea. And so this, so far, is not what we wanted, because here we have O of n squared features, the features coming from the deep sets of the off diagonals, that here you have n squared. So we want to reduce this to n times d. And the way we do that is using an idea from low rank matrix completion. The idea is that if we have the matrix of inner products is a low rank matrix, so it's a matrix of rank d, actually. So you can reconstruct all the inner products by observing d rows or d columns genetically. And so what we do is we construct basically we have to do something which is add some extra features which have to do with that can be constructed as the centroids of your points, or something that allows you to identify rows by permutation. And from that, you can reconstruct, you can construct an extra matrix that has extra columns that are constructed from your data points, the extra columns. And then from that, you can reconstruct the matrix of inner products from the last d row of your d columns or d rows of your matrix. And with that, you can write another machine learning model that actually has dependence on d times n on your data. So, and with that, you can reconstruct it. I'm not going to go into the details. I'll be happy to discuss it later. But basically, you can write a machine learning model that is also based on deep sets, that you can write it as the deep sets of some centroids times the original points and the matrix of inner products of the centroids. And with that, you can reconstruct. You can see that this model can universally approximate invariant functions on point clouds, and it has dependence of d times n in terms of d square, in terms of n squared. Okay, so we can apply this model to some problems in the QM7b, which is a molecular prediction model. And I'm not going to go into the numerical experiment details. I'd be happy to discuss it later if you are interested. Another experiment that we have uses this model data set based on point clouds. So you have this furniture. Each of these furniture, you can write it as point clouds. And then the regression task was to learn some distance between these point clouds using these machine learning models. In particular, the target here was something called the Gromov-Wasserstein distance between these point clouds. And we can see that it performs decently in comparison with some baselines. But maybe something that I should mention about these models is that if you are going to use the mathematical definition of these models based on just the invariant theory, you would use the symmetric polynomials on the diagonals and the off diagonals, and then you add another polynomial. These are polynomial functions on n choose 2 variables, which are the variables that define the symmetric matrix. In practice, we don't do that. We use deep sets. And one of the reasons why we use deep sets is because if you have a symmetric polynomial on n choose 2 variables, and you have a different number of points in your point cloud, you don't have a way to evaluate this symmetric polynomial because the symmetric polynomial has the number of variables that it has, and you cannot evaluate it on a different number of variables. But when we use deep sets, it allows us to write a function that can be evaluated on different number of on points with different on point clouds with different number of points, and that's something that is useful for machine learning. So what I'm going to talk about next in the last 5 minutes is like a formalism to understand machine learning models on different on varying size objects. So, and this is something that you may be familiar with because this is a fundamental property of graph neural networks, the fact that they can be evaluated on graphs of different sizes. If you see a graph neural network is on a fixed set of parameters, you can write a function that can be evaluated on any size graph. So in particular, one definition of these graph neural networks in this form, like you can write it in terms of your adjacency matrix. This is an n by n matrix times your node features. This is an n by d. But then the size of parameters is independent of n, the number of nodes in your graph, and that allows you to write functions that are independent of the number of nodes in your graph. And the same thing with the deep sets. The deep sets definition is independent of the number of elements in your set. So what are the underlying mathematical assumptions that allow us to do that? And what are we doing when you're learning machine learning model on different size objects? So in GNN, transferability is something that has been studied. And Juan is in the audience, and he has many papers on GNN transferability, and other people here as well. And the idea is that we can understand what happens when you train a GNN on graphs of 100 nodes and evaluate the GNN on graphs of 1,000 nodes. And basically, you're making an assumption, which is that if you have one way of understanding this is like by making the assumption that if you have a sequence of graphs, then this sequence of graphs are converging to an object, which is an infinite graph or a graphon. And then a GNN defines, if you have this sequence of graphs, one GNN with one set of parameters can be evaluated on all these graphs of different sizes and defines functions in each of these spaces with different number of nodes and in a way that is consistent. And the transferability comes from a form of continuity with respect to this sequence of graphs that converge to a limiting object. So you can define a theory of transferability that goes beyond graphs by thinking that if you have a sequence of vector spaces that are your inputs, in the case as the graphs where they live, and then you have a function that is defined as a machine learning model that has a fixed set of parameters, but it defines a function for each possible size input, defines a different function, then you can think of what happens with this sequence of machine learning models that are all based on the same set of weights. And you can, if you follow the theory of what the transferability of graph neural networks is saying, is that you have an embedding from the lower dimensional space to the higher dimensional space, and the machine learning model needs to be compatible with this embedding, meaning that it satisfies this equation. So embedding the graph in a larger space and then applying the model is the same as applying the model and then embedding the output space in the larger space. So that's what is called compatibility. And then continuity, which is transferability, is that in the limit, when n goes to infinity, this converges to a limiting model, and they're all continuous. And the choice of topology is important. So I'm not going to go into the details of like what topology you choose for each of these objects. So for instance, For deep sets, you can think of like how do you extend your sets? By adding zeros or by duplicating your objects. Each of them have a different norm and a different topology in the limit, and you can analyze the convergence. But maybe I'm going to just show you one plot for the GNNs, and I'm going to end with this. So for different GNNs, you can look at what does the GNN do when you make the graph larger, depending on how the model is normalized. So, and then you can have whether the model is compatible or transferable or not. Compatible meaning that the diagram commutes, and transferable means that the limit is continuous. So in this example, this normalized to a GN is not compatible. So if you look at what happens with the graph size going to infinity, you see that the model in the limit doesn't match the model in the different number of node graphs. So this is different from this because it's not compatible. And then in this example, this is compatible but not transferable. So compatible will tell you that this is flat. In the limit, this is flat. And the transferable will tell you that this line will converge to that line. I didn't go to the entire set of details, but I'll be happy to discuss it later. But that's basically the idea that I wanted to convey, that you can use the ideas from GNN transferability, extract what are the mathematical definitions that you need, and then apply it to different models, machine learning models that are defined on varying size of objects. And then something interesting that one can mention here is that when your models are equivariant with respect to a group action, there's something called representation stability that tells you that the number of parameters that you need to define all the linear equivariant functions stabilizes with the dimension. So that means that if you're looking at just the fn's being linear and equivariant, then you can define all these linear functions with a fixed set of parameters. So you don't have that you don't need that the number of parameters that define your model go to infinity. They can stabilize. And that's the reason why you can have universal models that are defining a fixed set of parameters, basically. That's the idea. So as a summary, I'm going to leave the summary here, and I'm just going to take questions because I think I'm out of time. Yes?
Do you have like a characterization of the bad sets in these theorems, like that stuff instead of the invariant function?
Yes, we don't have an exact characterization, but if you look at the proof of the theorems, you can get some form of characterization from it. So, for instance, in the case that I added here this f star, specific f star, this f star vanishes when the diagonal of the matrix is equal to 0. So then, if you have if you have graphs that have no loops, not self loops, then this is gonna give you a bad set. So in particular for graphs, this is not as expressive, but we expect that for point clouds and with the reduction of the from n squared to n times t, that may be useful. But yeah. So you can think of this is an invariant model on symmetric graphs, on symmetric matrices that represent weighted graphs, but actually, like this guy gives you something bad in the graphs with no self loops. How is this function what? So basically, you can think of like the field of functions generated by like this guy, and then adding that as a to your field. So you're adding an extra function, and then you're computing the field generated by this guy, that guy, and also that guy. So all the products, quotients, and linear combinations of functions of this form, and that form.